Right, for Ellingham diagram, right? This question is we start first by reading it. This part where highlighted in yellow color, ratio of hydrogen to H2O of the 10 power of 5. From here, we need to see the hydrogen part, silicon oxide trend line or the slope, as well as this line, which is the gray line of hydrogen, ratio of hydrogen over H2O. Following this line, it's line from here until right here. Okay, the gray line. Just follow the gray line. Gray with gray and the others with the others. Right, for example, you say is 10 to the power of 5. As you can see here, 10 to the power of 5 is around this part. And then they're asking for the trend line of silicon oxide. And from there, we just um, drag the line from H until from H here until this point, which is drag it by freehand, so it will be a bit not straight like that. So just drag it until you find this one, and then the point of intersection here or for the silicon oxide slope, we will drag the temperature down. We will extrapolate to get our temperature at this point. From here we get approximately 1000 something, 1000 maybe 1190 maybe something like that. This one can estimate, it's no problem. Around that can already. And then next one is they say discuss the stability of silicon oxide insulating layer based on the current temperature condition, which is the current temperature condition for us is 1190 degrees Celsius. From there, we see also this M right here is referred to the melting point for our metal, which is at 1300 400 something right here, right here. And then we compare with our 1190, which is it is still within the range for our not reach the our melting point yet. So we can say that our stability of silicon oxide is still stable due to the temperature is still within the range of the melting temperature. So it is stable. We can say like that. That one is the first question, the yellow one. The second one, what is the limit processing temperature that must be maintained in the furnace to prevent the composition of silicon oxide insulating layers? This one actually limits of processing temperature actually refers to the processing temperature itself of our silicon oxide, because the melting point itself for our silicon oxide from here we can change to green color. This one we can just drag here. Sorry, I erase first, more clear. Okay, so one our melting temperature for silicon oxide here, we just extrapolate it downwards to get our temperature. This one here you guys use ruler, this one I freehand. So it will be something like 1400 degrees Celsius approximately. And then this one refers to our limit of processing temperature, which is if our melting or our temperature that we apply is over this temperature, our metal will melt, which is our insulating layer of silicon oxide will also be gone due to the melting of the main substrate. So we can say that 1400 degrees Celsius is our limit processing temperature. That is the green color right here. And then the third question is the blue color. the oxygen partial pressure for oxidation at 1000 degrees Celsius. We find first the 1000 1000 degrees Celsius temperature, which is right here, this part. Then we just extrapolate it until we intersect with the our silicon oxide slope, which is right here. And then um, they want a partial pressure. So partial pressure is this part down here, the red one. So the red one need to refer to the O right here, also red color. So from there, we will make our straight line from O intersect with our blue color right here at temperature 1000 until we meet the partial pressure at our partial pressure axis right here. So from here I just drag it down. This one I just using freehand, so you guys need to use it using a ruler better for you to get the value. So from here you just drag it down, then you get some value right here. This one maybe not correct, but the technique is like this. So you using a ruler to get your partial pressure at the temperature of 1000 degrees Celsius, which is by referring to the senior answer right here, he get about um yeah, this one, 10 to the power of negative 26. We will get around this value for our partial pressure at the temperature of negative at temperature of 1000 degrees Celsius. So you just drag the line until you get some value here, which is this value intersect right here is our partial pressure at the temperature of 1000 degrees Celsius. It's about 10 to the power of negative 26. So settle the third question. And then the last question for A2, which is the pink color. I don't know the color. Is the pink or yeah, right? And then at what partial temperature will silicon oxide be reduced to pure silicon? Which is this one. It's actually silicon oxide will be reduced at silicon. So refer back to our melting point for our silicon slope right here. Then we also repeating when they say about partial pressure, we will refer to the O on the left side and also the axis of partial pressure right here. So make sure our drag our line from O, we'll drag and then we intersect with our melting point at our silicon slope, and then until we intersect with the other axis of our partial pressure at the end here, which is we will get our partial pressure that will reduce the silicon oxide into pure silicon is at partial pressure of 10 to the power of negative 19, something like that, around here. But the senior got 10 power negative 16. This one still acceptable, still in the range we can say. But if we use properly the ruler, we may got this kind of value. Then settle with the A2 question. Moving on to the third question, which is they're asking about the carbon monoxide to ratio of carbon monoxide and carbon dioxide pressure ratio of chromium oxide. This one not about silicon oxide already. This one is chromium oxide. From here, we finding the chromium oxide slope first, which is right here. This is the slope for chromium oxide. And then they say the ratio of CO over CO2 at temperature of 300 degrees Celsius. So we look back our temperature axis, which we find the 300 degrees Celsius, which is around this area actually, and then we will interpolate or extrapolate the line until it's intersect with our chromium slope right here, this point. Then for carbon, CO2 over CO over CO2 ratio, we see from left side is the C right here, and also for this axis on the right side is the axis here, CO over CO2. Then the same step, we will drag the line intersect with this point at 300 degrees Celsius, and then we drag until we meet the carbon CO over CO2 line axis. So our ratio of CO over CO2 is about 10 to the power of 9. Yeah, personally. This one settle our question, the red one. And then they say it's the last one. Oh, the last one is carbon good reducing agent at this temperature, which is they are referring to the temperature of 300 degrees Celsius just now. Then they say carbon. So actually the carbon is right here. Carbon is right here, and if referring to the temperature of 300 degrees Celsius, it will be here. The rules for the slope that can be a good reducing agent is that, for example, we want to reduce the chromium oxide right here. The slope that better that we can choose is the slope that under the chromium itself. For example, we can choose mangan right here, or silicon right here, or even titanium right here to reduce our oxide. But for this case, they're asking whether the carbon is the good reducing agent, which is the carbon position at this temperature is actually above the chromium. For this one, we can say that carbon is not a good reducing agent at this temperature of 300 degrees Celsius. So we can also suggest that we can use mangan or even silicon to as our reducing agent for chromium oxide right here. So that's the way how we solve Ellingham diagram question. Okay, please subscribe.